Hi, this is the third video in gas laws. Well, we've already seen how pressure and volume are related with Boyle's law and how the temperature and volume are related with Charles' law. There's another law called Avogadro's law. If you're keeping your pressure and your temperature constant, the volume of your gas is going to be directly proportional to the number of moles of gas that are present. When we put Avogadro's law, Charles' law, and Boyle's law all together, we come up with something called the ideal gas law. Now, ideal gas laws, there are two different forms that I like to use. The first one is the most common form. PV is equal to nRT. So let's have a look at what P and the V and everything means in here. So P is pressure, and remember we have all those different units for pressure. V is volume, and our volume when we use this gas law has to be in liters. N is moles, I hope we learned that. R is the gas constant, and there are many different forms of R, and we'll come back to that. And T is temperature, and that must be in Kelvin. All right, let's talk about the gas constant R. If you notice, all of them have these really long units. So 0.0821 liters times atmospheres divided by moles Kelvin. All right, if your pressure in this equation is in atmospheres, this is the value of R that you will use. Now, if you look at the next value of R, 62.4, notice the only thing that's different from the other R is the unit of pressure. And if your unit of pressure is torr or millimeters of mercury, the value of R that you would use and plug into the equation is 62.4. If your pressure unit is kilopascals, the value for R is 8.314 liters kilopascals per mole Kelvin. This gas constant, this R, is what drives this whole equation, and it pretty much dictates the units that you have to use. Your volume has to be in liters because R is in liters. Your temperature has to be in Kelvin. R is in Kelvin. And then whatever pressure unit your R is would be the pressure unit that you would end up with in your ideal gas equation. Or if you're given a pressure in atmospheres, you'd use this R. If you're given a pressure in kilopascals, you would use the value 8.314. All right, so this is the most common form of the ideal gas law. Now, when we talk about ideal gases, we're, oh my goodness, it says idea. Ideal gas law. What we're talking about is a gas that behaves as if there are no other gas molecules around it, which isn't always the case, but it's a pretty good assumption. The other form I like to use is PM is equal to DRT. And this capital M stands for molar mass. And remember, molar mass, the unit is grams per mole. And then the D is density, and density by definition is mass per unit volume, and the units would be grams per liter. So what we're going to do is we're going to work three problems using these two ideal gas equations. Mainly, you just have to get all your units, in the right form. Make sure you're using the correct R, plug your numbers in, and get an answer. All right, so our first problem is we have a gas under a pressure of 74 millimeters of mercury. So I like to go ahead and I like to write everything down. My P is 74 millimeters of mercury. The temperature is 75 degrees Celsius. Well, that won't do. We've got to immediately convert that to Kelvin. So plus 273 is going to be 348. Kelvin. And then our volume is, it's already in liters. It's a really big container. It's 500 liters. All right, and then we like to know how many moles do we have. All right, so it looks like we've got a P, a V, an N, and a T. So we're going to use this form of the gas equation. All right, now, what R will we use? Well, let's look at our pressure unit. Our pressure unit is in millimeters of mercury, so the R that we have to use is 62.4 liters, millimeters of mercury per mole Kelvin. All right, my volume is in liters, yes. My pressure is millimeters of mercury, yes. I'm solving for moles. My temperature in Kelvin, yes. Okay, so let's go ahead and plug these numbers in. All right, so 74 millimeters of mercury times 500 liters is equal to N. That's what we're solving for. The R that we've chosen to use based on our pressure unit is 62.4 liters, millimeters of mercury per mole Kelvin. And our temperature is 348 Kelvin. Okay, we are done with the chemistry here. Now all we have to do is the math. And so N is going to be equal to 74 times 500 divided by parentheses 62.4 times 348, end of parentheses, and the value you get for N is 1.7 moles. Now it's important that you plug these numbers into your calculator to make sure that you're putting them in the right way. And be sure that you can solve for this N using your algebra. It's easy to make mistakes. All right, the next problem. An unknown liquid is vaporized at 100 degrees Celsius. So our temperature is 373 Kelvin. And it fills a volume of 25 milliliters. Well, our volume always has to be in liters. And so remember, milliliters to liters, you divide by 1,000. So 0.025 liters. Our pressure, again, is in torr this time, 750 torr. And then all of a sudden they tell us a mass. So our grams is 0.0564 grams. They want to know the molar mass, capital M. All right, well, we're going to have to use the equation that has molar mass in it, which is PM is equal to DRT. We have a pressure. We're solving for molar mass. Ooh, density. Density is mass divided by volume. So let's go ahead and calculate our density. Our density is 0.0564 grams, and our volume is 0.025 liters. And when I do that, our density is 2.26 grams per liter. Okay, so we got our density. What R will we use? We have the pressure unit torr, and so the R that we need to use is 62.4 liters torr per mole Kelvin. And our temperature is in Kelvin, so we're good to go. All right, so now we are going to plug in our numbers and solve for our molar mass. All right, our pressure is 750 torr. We are solving for our molar mass. Our density is 2.26 grams per liter. Our R value is 62.4 liters torr mole Kelvin. Our temperature is 373 Kelvin. All right, to solve for our molar mass, you are going to multiply 2.26 times 62.4 times 373, and then divide it by 750, and we come up with a molar mass of 70, and our units are going to be grams per mole. Everything else will cancel. The liters canceled, our kelvins canceled. When we divide by the torr over here, it will cancel, and we're left with grams per mole. All right, our final problem. What is the pressure? And they would like it to be in atmospheres. So they want the P in ATM. is exerted by 0.1 moles of a sample. So N is 0.1 mole, and it just happens to be oxygen. Our volume is 2 liters, and our temperature is 273 degrees Celsius. We have to add another 273 to it to convert it to Kelvin, and it winds up being 546 Kelvin. All right, they would like us to solve for P. So they want our P to be in atmospheres, and so the R that we're going to use is the 0.0821 liters atmospheres per mole Kelvin. All of these R values are given to you on your reference sheet. The way you choose the R is by looking at the unit of pressure that you need, and then you choose the R that has the same pressure unit. All right, so here we go. So P times V, it's in liters, that's good because our R is in liters, is equal to N, they gave us moles. R, we said we need to use the 0.0821 liters atmosphere mole Kelvin. And our temperature is 546. Now, we'll multiply 0.1 times 0.0821 times 546, divide all of that by 2, and we'll come up with a pressure of 2.2 atmospheres. Okay, so that's it for the ideal gas equations that we're using. And so we just have to really be careful of our units, making sure that our units are matching the units in R, that we're choosing the proper R with our pressure unit, and then we just plug the numbers in and make sure we do the algebra right, and you should get the right answer. All right, we'll see you tomorrow.